Just as we found the real form of Newton's second law is not sum of the forces equals ma, it's really sum of the forces is dp dt, it turns out that sum of the torques equals I alpha isn't exactly right. What we should have instead is sum of the torques is dl dt, where L is angular momentum, and we can define that as either I times omega, or for a point particle, we usually say L is r cross p. The product rule gives us two terms here, just like before. So d dt of I omega is I d omega dt plus omega di dt. If we don't have any change in the mass distribution or the shape of an object, the second term goes away, and we end up with I alpha for the sum of the torques. The change in the second term, the di dt, this would happen if you have something like, for example, a figure skater pulling her arms in. That changes the moment of inertia, and since momentum is conserved on the low friction ice, or angular momentum is conserved, you would see that a reduction in moment of inertia leads to an increase in angular velocity. So if the sum of the external torques is zero, we'll have conservation of angular momentum just like we had conservation of linear momentum when the sum of the external forces is zero. Let's imagine we have a disk resting on a frictionless surface and we fire a bullet at the edge of the disk. This is going to cause a rotation. What we need to look at this, we need the moment of inertia for the disk, which is 1/2 mr squared. We've got the mass and radius for the disk. And then we need to know the particulars for the bullet, the mass and its initial velocity. For the point mass of the bullet, we find the angular momentum using r cross p, which is mvr sine theta. If the bullet hits the disk right at the edge, then there's a 90-degree angle between mv and r, and sine theta would be 1. So we get an initial angular momentum coming entirely from the bullet of mvr, or 3.9375 kilogram meter squared per second. Notice that the bullet does have angular momentum even though it's traveling in a straight line. It's not rotating at all because, as seen from the center of the disk, it is moving in a rotational way. After the collision, final momentum is IF omega f, where IF is angular, or the moment of inertia of the disk and the moment of inertia of the bullet. For a point mass, moment of inertia is mr squared, where r is the distance from the point mass to the rotational axis. And we figure this out. We get the disk's contribution and then the bullet's contribution. Notice I can't just add the bullet's mass to the disk's mass because we only get 1/2 for the disk, but the full mr squared for the bullet. Anyway, we get 0.4624 kilogram meter squared. So I can say omega final is angular momentum final over moment of inertia final, but the final angular momentum is the same as the initial, so I can do 3.9375 divided by 0.4624, and I get 8.515 radians per second. So this is how fast the disk-bullet combination is spinning. This collision is completely inelastic since the bullet sticks, and we can look at the kinetic energy before and after. Before, it's entirely translational. We get a very large amount, 2531 joules. Afterwards, it's entirely rotational, and we get only 16.76 joules. Again, kinetic energy is not conserved here, but of course, total energy would be. We can do another example, another disk, and on a frictionless surface, but this time we put a bug on the disk, and it's a very large bug, 0.28 kilograms, and it's about 2/3 of the way out from the center, 0.15 meters on a 0.22 meter disk. If they're both initially rotating at 7 radians per second, what happens if the bug moves out to the edge of the disk? This is a similar problem to the figure skater. If you start with your arms tucked in and move your arms out, what will happen? So we solve this the same way. We say the initial angular momentum is initial moment of inertia times initial angular velocity, and then the initial moment of inertia is I disk plus I bug at that distance, the starting distance. We get 0.0426 kilogram meter squared. For initial angular momentum, we multiply initial moment of inertia times initial angular velocity. We get 0.2982 kilogram meter squared per second. At the end, this would be the end of the collision because this is an exchange of momentum. The bug moves, so I changes. So I final is, nothing's changed for the disk, But now, for the bug, things have changed. The position has changed. So moment of inertia goes to 0.04985. Just like before, the final angular velocity is final angular momentum over final moment of inertia, but that's the same thing as initial angular momentum over final moment of inertia. We get 5.98 radians per second, so the disk slows down, which is what would happen to the figure skater as well. Just to see what the kinetic energy looks like, initially 1/2 I omega squared, since it's all rotational, 1.044 joules. At the end, again it's all rotational, but we have a different I and a different omega, 0.891 joules. Usually, final kinetic energy is less than initial kinetic energy, but what happens if the bug moves closer to the center? What if it comes to within 5 centimeters of the center? We've got a new moment of inertia. It's the disk, which hasn't changed, plus the bug's new moment of inertia, which is much smaller, so our total is smaller. When we do this, we get final angular momentum when the bug is close in. Our final angular velocity when the bug is close in moves up to 8.06 radians per second. If you find the kinetic energy at this point, you notice that it's now 1.202 joules. That's larger than either at the start of the problem and certainly larger than where it was when the bug was at the edge. Where does the energy come from? It actually comes from the bug. The bug is going to feel a centrifugal force, which is fictitious, but we can calculate with it, of mv squared over r trying to throw it off the disk, and the bug will have to work to move against it. So we can use the work energy theorem. The force is outward if we use centrifugal, but the displacement is inward, so we're going to get a negative, but we're going to integrate from 0.35, where the bug started, to 0.05, where the bug ended up. And when we do this math, actually that 0.35 should be 0.22. It's correct down here though. When we do this math, we get 0.309 joules for the work done by the bug, and if we add that to the kinetic energy at the edge, we get 1.201. So you can see where this integral came from. The only error is this 0.35 should be